Welcome to my talk about red-blue geometric covering problems. Geometric set cover, the geometric version of set cover, is a fundamental theoretical problem that has been studied for over 30 years. In this version of set cover, we are given a set of points and a family of objects, and the goal is to select minimum number of these objects to cover all the points. This problem is NP-hard even for simple geometric objects such as unit squares and axis-aligned rectangles. If the objects are axis-aligned rectangles or triangles, then it has been shown that the problem is also APX-hard. In the red-blue version of this problem, a red-blue set and a set of objects are given. This time, the goal is to cover all the blue points while minimizing the number of covered red points. This problem is NP-hard even when the objects are axis-aligned unit squares. While geometric set cover has been studied widely for several geometric objects, the red-blue version of this problem has been studied only for axis-aligned unit squares, and no hardness of approximation or approximation algorithm were shown before for the other objects. Let me remind you the relation between the red-blue version and non-red-blue version of this problem in non-geometric setting. If we have an instance of set cover, a set of elements X, and a set of subsets of this set T, we can reduce this problem to red-blue set cover with the idea of considering all the elements of X to be the blue elements in the red-blue version, and then add exactly one distinct red element to each subset. When we are minimizing the number of covered red points, we are also minimizing the number of selected subsets. So we are answering the set cover. The main question in our study is whether such a relation exists in the geometric version, or if at least we can say the red-blue version is harder in geometric setting. In the geometric version, no such a relation has been shown before. We are specifically interested to see if there is a relation between these two problems when we are studying the same type of objects. It is also easy to observe that the same idea of the reduction, which was adding one distinct red element to each set, does not work in the geometric setting. It is not always possible to find a space to add a distinct red point in these objects, as one red point might be covered with more than one object, although that we couldn't find an idea to reduce a non-blue version to the red-blue version, we could still compare these two problems by asking whether approximating the red-blue version is harder. To answer this question, we prove that red-blue geometric set cover when the objects are axis-aligned rectangles is APX-hard. And we do this by reduction from max RM3 set, a newly defined version of max3 set. And we show that we can modify this reduction to show a closely related problem. Box's class cover is also APX-hard. Our second result is the red-blue geometric set cover when the objects are convex objects or even triangles is as hard as red-blue set cover. We can show our first result in two ways. The first way is by showing a reduction from a special 3 set cover to this problem. And this is a modification on the reduction that was originally used to show that geometric set cover for axis-aligned rectangles is APX-hard. And the second way is by showing the reduction from max E3 set 5 to max RM3 set, which I will define later, and then reduce this problem to red-blue geometric set cover for axis-aligned rectangles. In this talk, I will talk only about the second way, and I will also talk how we can modify this reduction to show Box's class cover is also APX-hard. To show a reduction from max E3 set 5 to max RM3 set, let me first define these two problems. Max E3 set 5 is a version of 3 set where each clause has length 3 and each variable appears exactly 5 times. This problem has been shown to be APX-hard. And the problem of max RM3 set, restricted mixed 3 set, is a version of 3 set which each clause has length maximum 3, and all the clauses of size 3 has a negated and one non-negated literal, which means we cannot have all negated or all non-negated literals in one clause, and also each variable, for example x, can appear exactly once in clauses of size 3, and even x negated cannot appear if x was appeared. And the third condition is that each variable appears exactly once in the clauses of size 2 in negated form and once in the clauses of size 2 in non-negated form. To show that this very restricted version of 3SAT, max RM 3SAT, is also APX-hard, we reduce max E3SAT5 to this problem. If you have an instance of max E3SAT5 with m clauses, then we take all the clauses of size 3 in this formula and add to the clauses of max RM 3SAT problem. By just changing the name of the variables, for example, if this is the ice time that we are seeing variable x, we will call it xi. And then we will add some clauses of size 2 to make sure that all the instances of xi has equal assignment. In this way, we could show a relation between the number of satisfied clauses in these two formula and show that the problem of max RM 3SAT is APX-hard. Now that I showed the first part, I need to show how we can reduce max RM3 set to red-blue geometric set cover. If you have an instance, a formula with 4m clauses and 3m variables, we want to show how we can create a point structure with red-blue points and 11 rectangles, and then show a relation between the number of satisfied clauses in this maximization problem and the number of rectangles in this minimization problem. In this point structure, each layer is for one variable. For example, in this picture, the 4 blue points in the shaded area is for variable x2. And we also add 2 horizontal and 2 vertical rectangles in the set of the rectangles and add one distinct red point to each of these rectangles. As you can see in this structure, if we want to cover all the blue points, we never can cover a blue point from one variable with a rectangle for another variable. So we need at least either 2 vertical or 2 horizontal rectangle for each variable. So the main idea of the reduction is the choice of vertical versus horizontal rectangle, which corresponds to true or false assignment for that variable. We also need to add some extra points for each clause depending on the structure of that clause to force the choice between vertical and horizontal rectangles for each variable. For example, if the clause is x1 or x2, we will add some extra points in the green area in a way that if the clause is satisfied, it means that at least one of these variables is true and we picked at least one of the vertical rectangles for x1 or x2, then we are covering at least one of the blue points for this structure, and we would only need one extra rectangle to cover the other 2 blue points. And if the clause is not satisfied, then we would need 2 extra rectangles. This gives us a relation between the number of satisfied clauses in this maximization problem and the number of rectangles in this minimization problem. And by considering the fact that we could always find the area to add one distinct red point to each rectangle, then this means minimizing the number of red points would also minimize the number of rectangles, and we could show that the red-blue geometric set cover is APX-hard. There is a closely related problem, boxes class cover, in which a red-blue point set is given, and the goal is to find the minimum number of Acis-Aligned rectangles to cover all the blue points, but no red point. The difference between this problem and geometric set cover is that in this problem, the set of the rectangles is not given, and we can pick from all the possible Acis-Aligned rectangles, and also we don't want to cover any red point. The problem is a special version of set cover, and it has been shown that is NP hard, but no hardness of approximation was shown before for this problem. We show that we can modify our reduction that I just explained from max or M3 set to this problem to show that this problem is also APX-hard. And the idea is just keeping the same structure for the blue points and the same red points, but we are going to add more red points to restrict the choice of these axis-aligned rectangles to be the ones that I just explained in the previous reduction. Now I will talk about our second result, which is about red-blue geometric set cover when the objects are convex objects. I want to show that we can reduce red-blue set cover to this problem. If we have an instance of red-blue set cover, which is a set of blue elements, a set of red elements, and a set of subsets of these two sets, I want to show this point structure, which we first consider a circle, and then we will add one blue point for each blue element and one red point for each red element on this circle. And then for the convex objects, we add the convex hull of the points related to the elements of each subset to the set of convex objects. For example, this is for the first subset, and we are sure that we can do this for any given subset without covering points from the other subset because we are putting these points on a circle. In this way, when we are minimizing the number of covered red points in the geometric version, it is obvious that we are answering the non-geometric version. And this shows that the problem of red-blue geometric set cover for the convex objects is as hard as red-blue set cover. We also show that we can have the same result even when the objects are triangles, and this comes from the fact that the original result for the red-blue set cover holds even in the restricted case that each set contains only one blue and two red elements. We can have the same point structure that I just described, and then we are sure that we can cover any two red and one blue point with a triangle without covering any other point, and this shows that the problem of red-blue geometric set cover even when the objects are triangles is as hard as red-blue set cover. By considering these results, let's compare geometric set cover and red-blue version of this problem again. We know that we can reduce geometric set cover to set cover by an easy observation that we can write all the points that one object covers as the subset and each of the points as the elements. And also I mentioned how we can reduce set cover to red-blue set cover by adding one distinct red element to each subset. And we also showed that how we can reduce red-blue set cover to red-blue geometric set cover when the objects are convex objects. So we kind of showed that geometric set cover can be reduced to the red-blue version of this problem, but the problem is that we didn't use the same type of objects. For example, if we start with axis-aligned rectangles, we are not reducing it to the same problem in the red-blue version. We are using convex objects in the red-blue version. But we are interested to know what happens if we are using same type of objects. To answer this question, let me compare our results with the previous results for geometric set cover. So if the objects are axis-aligned rectangles, it was shown that the geometric set cover is APX-hard, and we showed that the red-blue version is also APX-hard, which means it is as hard as the non-red-blue version. And when the objects are triangles, it was shown that the problem is APX-hard, and also there is this log of optimal epsilon net based approximation algorithm. So if we compare this with our results, we can see that the hardness we showed for the red-blue version is greater than the approximation factor that we can get for the non-red-blue version. This shows that there is a class of objects, triangles, for which approximating red-blue geometric set cover is strictly harder than geometric set cover. For the future work, it seems that we can show a better hardness of approximation for the red-blue version when the objects are axis-aligned rectangles. We are also interested to study the problem when the goal is to minimize the ratio of the covered red points to the covered blue points instead of the number of red points.